Hello and welcome to the last part of the unit Electrolysis Principles, where we conclude by explaining the high-temperature electrolysis technology. We present now the high-temperature electrolysis technology, mainly known as solid oxide technology, and which is characterized to work between 800 and 1000 degrees Celsius. Here, the solid electrolyte is an oxygen ion-conducting ceramic material. This ceramic material can prevent corrosion due to its material properties at such high temperatures. Ceramic electrolyte based on zirconium have been selected to be used in this type of electrolyzers. This material shows a high conductivity for oxygen ions and operating temperature, and the most commonly used is hydrogen and calcium stabilized zirconia oxide. The electrode and electrolyte materials, as well as their geometry, can change depending on the operating temperature in order to optimize their performance. The electrochemical splitting reaction of steam at high temperature can be described by the half-cell reaction, which appear in the figure. As we can see, at the cathode, steam is introduced, and thanks to the electrons provided by the DC power source, the water molecule breaks it down into hydrogen and oxygen ion. Hydrogen is extracted as a product, and oxygen ions move towards the anode through the electrolyte. At the anode, the oxygen ion releases the 2 electrons and it is transformed into oxygen. Due to the high temperature at which this type of electrolysis cell works, the water has to be heated up and form steam before entering the cell. High-temperature electrolysis presents several characteristics, including its very low electricity consumption. This can be achieved by using high temperatures supplied by high-temperature nuclear reactors or solar concentrate energy. Furthermore, it consumes about 3 kWh of electricity for every 1 normal cubic meter of hydrogen produced, being the electricity demand at 100 degrees Celsius 30% lower than that required at room temperature. Therefore, the decrease in the required electrical energy results in greater efficiency in the conversion of thermal energy to hydrogen. In addition, high temperature also favors electrode activity and helps reduce cathode and anode overvoltage. In this way, it is possible to increase the electrical current density at high temperature and decrease polarization losses, which increases the efficiency of the process. In conclusion, we can say that high-temperature electrolysis is advantageous both from the thermodynamic and kinetic point of view. The figure shows a 3 electric kilowatt-size pressurized high-temperature electrolysis system coupled to a concentrated solar energy source developed by the European project SOFIA. In this process, the steam is decomposed into hydrogen and oxygen at high temperature in the range of between 700 and 800 degrees Celsius, and using a combination of electrical energy and high temperature heat. This system can produce carbon-free hydrogen using electricity from CO2-free energy sources on large scales, and it has the advantage of higher hydrogen production efficiency in comparison with the conventional low-temperature electrolysis. However, despite their multiple advantages, the development of a practical electrolysis process with a solid oxide electrolysis cell is still in the early stage. The main objectives of the research are currently the reduction of production cost, the improvement of efficiency, and mainly the duration of electrolytic cells. With this, we conclude this unit that brings together the principle of electrolysis. Thank you very much for your attention.